Bismillah wa salatu salam ala Rasulullah. Today, I will present my project about DC motor modeling and control using MATLAB Simulink. In this project, we derive the transfer function of the DC motor and analyze its response using different controllers. So let's move to the next slide to see the introduction. So, DC motor. This project discusses the mathematical modeling of a DC motor and the derivation of its transfer function. The DC motor converts electrical energy into mechanical rotational motion, and it is widely used in control systems and industrial applications. In this slide, we first show the equivalent circuit of the DC motor. The circuit contains the input voltage, source, armature resistance, armature inductance, and the back EMF generated by the motor. When voltage is applied, current flows through the armature winding and produces rotational motion in the motor shaft. Next, we define the main motor variables and parameters used in the mathematical model. The input voltage is plus or minus 24 volts, and the desired motor speed is 100 radian per second. R represents the armature resistance. L represents the inductance. G is the inertia. B is the damping coefficient. T and E is the are the motor constants. In this slide, we define the main motor parameters and variables as we said here, such as resistance, inductance, inertia, damping coefficient, and motor constants. We also apply Kirchhoff's voltage law to derive the electrical equation of the motor circuit. So, after defining the variables here, we apply Kirchhoff's voltage law to derive the electrical equation of the motor circuit. According to Kirchhoff's law, the input voltage equals the sum of all voltage drop in the circuit. So the equation includes the resistor voltage drop, okay, and inductance voltage drop, and the back EMF voltage. In this slide, we apply Laplace transform to convert the electrical equation from the time domain into S domain. This makes the mathematical analysis easier and helps us derive the transfer function. So, as you see this equation represents the electrical equation of the DC motor in the S domain. The input voltage equals the sum of three terms. The first term represents the voltage drop across the armature resistance. The second term represents the voltage drop across the armature inductance. The last term represents the back EMF voltage generated by the motor rotation. Here, the back EMF voltage is proportional to the motor speed, where Ke is the back, Ke, this one, is the back EMF constant, and omega of S is the angular speed. Finally, we combine the resistance and inductance terms together to simplify the equation. This simplified equation will later be combined with the mechanical equation to derive the transfer function of the DC motor. So, I mentioned here we apply Laplace transform, as I said, to convert the electrical equation from the time domain into the S domain. This simplifies the analysis and allows us to represent the system mathematically using transfer functions. So let's move to the next slide to see what we have. In this slide, we derive the mechanical equation of the DC motor using Newton's second law of rotational motion. So, this equation describes the relationship between torque, inertia, damping, and motor speed. We have here According to Newton's second law, the sum of torques equals the inertia multiplied by the angular acceleration. So here G represents the motor inertia and d of omega of t, d of t represent the angular acceleration. So here in this equation, the motor torque means the dampened torque equals the inertia torque. The term P of omega represents friction and dampen inside the motor. Here, after applying Laplace transform, the equation is converted into the S-domain for easier analysis. And finally, we rearrange the equation to express the armature current in terms of motor speed. This equation will later be substituted into the electrical equation to derive the final transfer function. So let's move to the next slide to substitute all the equations together. In this slide, the electrical equation and the mechanical equation are combined together, okay, to derive the general transfer function of the DC motor system. So this equation, here we substitute the mechanical equation into electrical equation. So this equation now contains both the electrical parameters and the mechanical parameters of the motor. Second equation, we simplify the equation by combining all terms together into one expression. The last equation we have, we rearrange the equation to obtain the transfer function of the DC motor. The transfer function represents the relationship between the output voltage, okay, between the output motor speed, and the input voltage. So this mathematical model will later be used in MATLAB Simulink to analyze the system response. As I mentioned here, the electrical and, as I said, like in the first, the electrical and mechanical equations are combined together. So let's move to this slide to explain all the substituted values that has been given in the question, in the requirement. So the given motor parameters are substituted into the transfer function equation. The values include the armature resistance, inductance, inertia, damping coefficient, and motor constant. So this is the general transfer function equation before substitution. Next, we substitute all the motor parameters into the equation. Here, after multiplying and simplifying the terms, we obtain the denominator polynomial. So finally, after adding the last constant term, we obtain the final simplified denominator of the transfer function. Let's move to the final transfer function. So in this slide, we obtain the final transfer function of the DC motor system after simplifying all the electrical and mechanical equations. This transfer function represents the relationship between the output motor speed and the input voltage. So the numerator represents the motor gain, this one, while the denominator represents the dynamic behavior of the system. Using this transfer function, we can analyze the stability and response of the DC motor. So now we have the simulation part. In this part, the DC motor system will be implemented in MATLAB Simulink to analyze the system response and test different controllers such as P, PI, and PID controllers. So let's move to the MATLAB application. Now we have the simulation part. First of all, we have to add the step signal. And then we will put this like 100 as a desired speed. So I will call this line the desired speed. Okay, and this line, the output coming from here, I will call it the actual motor speed. Okay, correct that. Yes. And if you wanted to see the results in this screen, you have to put and add the dashboard scope. Okay. And then add the lines, double click on the dashboard and add these lines and this line as a desired speed and actual speed. Let's apply it in this dashboard. And we also, like, first of all, I will apply the PID controller. So after a lot of tests and calculations, I found these three values like the best for the overshoot and the stability. Yes, as you can see here, this is the desired speed colored by the orange, and this is the actual motor speed, So the overshot, like I calculated as 6%. It's a smaller value, and it comes before 2 seconds. Like the rise time is less than 2 seconds. So this is the requirement for the report. So this is for the PID controller. Let's test the PI controller. Like, we will set that as a PI, and we have proportional and integral. Yes, that's it. As you can see here, the actual speed, the desired speed is 100, and the actual motor speed is 100, the same. And the overshot here is 6.25%. So, and the rise time is less than 2. So it's fine. This is for the PI controller, as you can see here. And then apply the P controller. Like hardly work how to make a stable system for it. I found the value, but the overshoot is around 25.8. So the value for the proportional is 80. So we will apply that and see what it comes. Let's run that. So as you can see here, this is the best results that I have received from the experiments. This is the experiment, this is the output, and thank you, and I hope you everything is clear in this presentation.